I'm Alan Fenn at MIT Lincoln Laboratory, and this is lecture number 13, Arrays of Horizontally Polarized Omnidirectional Elements. This lecture is part of the lecture series Adaptive Antennas and Phased Arrays. Here's course content breakdown by topic. This is lecture number 13. We'll be covering some phased array theory, antenna measurement techniques. We'll be taking into account array mutual coupling, and we'll be investigating far-field characteristics. Chapter 13 of the book Adaptive Antennas and Phased Arrays for Radar and Communications contains material that could supplement this lecture. So the purpose of this lecture is to describe measurements of an array of horizontally polarized omnidirectional antenna elements for wide-angle scanning applications. Here's an outline of the talk. After a brief introduction and background, I'll describe the methods and materials, some results, and then summarize. So by way of introduction, adaptive phased array antenna systems have been explored extensively by numerous researchers since the 1950s. And the primary functions of a phased array antenna system are to provide rapid beam steering, in some cases multiple phase centers, and low side lobes. This slide shows an example antenna element gain pattern with a null at broadside. So in some applications, an array element can have a pattern that has a null at broadside and is omnidirectional in azimuth. So for the example shown here, the array would be assumed to be in the XY plane, and it would have a shaped elevation pattern, and it would be omnidirectional in azimuth. And so one application for a phased array antenna that would require wide-angle steering with a null at broadside would be the case of a space-based radar in low-altitude orbit. So the antenna would not try to steer the radar energy directly below the space-based radar, since the high grazing angles at the Earth would create a large amount of clutter, which would dominate over any moving targets. So a null in the antenna element pattern would be beneficial. We do want the antenna to have a maximum or a peak element gain pattern toward the horizon. And so the phased array radar would steer a beam between the maximum cone and the minimum cone, and it should have uniform coverage in azimuth. So an array that has omnidirectional vertical polarization is a monopole array. It's a photograph of a monopole array shown here, and this was covered in detail in lecture 9. So a monopole array consists of typically a quarter wavelength radiator over a ground plane, and the typical pattern of an element is shown here, where it has a null at broadside and a shaped elevation pattern and is omnidirectional in azimuth. Another way to generate this type of radiation pattern with horizontal polarization is to use something referred to as a uniform current loop antenna. So this would consist typically of two swept back dipoles that are fed 180 degrees out of phase, forming a current that would flow around the perimeter of this loop. At the ends of the dipoles, they can be tilted inward so that they couple, and they can be used in tuning the antenna. So the feed point's in the center. We have a coax cable coming up through the ground plane. The center pin is connected to one side of the transmission line connected to the two dipoles, and the outer jacket of the coax near the feed region is connected to the other conductor. And so there's a microstrip feed line feeding these two dipoles. So a uniform current loop antenna could be considered for an application where a null is desired at broadside and wide angle coverage away from broadside. Another type of antenna element that can be used would be a loop-fed slotted cylinder antenna, where we take the same type of uniform current loop and now place it inside a conducting cylinder with a number of slots cut in it, a number of vertical slots. So the electric field would be horizontal inside the slots, And the radiation pattern would have a null at broadside and wide angle coverage away from broadside. So in this lecture we'll be concentrating on the loop-fed slotted cylinder antenna. Let's now talk about the methods and materials. So in this lecture we'll be talking about array mutual coupling and element gain patterns for the loop-fed slotted cylinder antenna. So in this diagram we have an element driven in an array environment. So the element will couple into the surrounding neighbors. If we have an input signal at the central element, it would couple into the other surrounding elements, which would normally be terminated in 50 ohm matched loads. We can measure the coupled signal into one of the elements, and that would be referred to as S0n, where 0 refers to the reference element, and n is the nth element where the coupled signal is measured, for example. We also want to determine the element gain pattern in the presence of the surrounding neighbors, and that's G sub E as a function of theta and phi. So in summary, S0n is the coupling from the center element to the nth element of the array, and G sub E of theta phi is the element gain pattern typically for the center element of the array. And this topic was discussed in detail in Lecture 8. This slide shows a loop-fed slotted cylinder antenna on a ground plane. The ground plane has dimensions 1.22 meters on a side. The loop-fed slotted cylinder antenna is located at the center of the square ground plane. And so the principal polarization would be the E phi component for the slotted cylinder antenna, and E theta would be the cross polarization for this antenna. And so, as shown in this diagram, the loop-fed slotted cylinder antenna or array of antennas would be located in the XY plane, and the Z direction would be the direction in which the element has a null. This slide shows two arrays that were built. One array is a 7-element hexagonal array, and the other is a linear array. So we'll be measuring the performance of the central element of the array. In both cases, we'll measure the mutual coupling to the surrounding neighbors. We'll show the element gain patterns and return loss. So let's show some results. Here's the measured return loss of a single loop-fed slotted cylinder antenna on the 1.22 meter ground plane. And the return loss from 1.2 to 1.4 gigahertz is below about 10 dB across the band. So the antenna has a good return loss, a good impedance match. Now we can measure the gain pattern of a single isolated loop-fed slotted cylinder antenna on the ground plane, and that's shown here over the band 1.2 to 1.4 gigahertz. This is a 15% bandwidth centered at 1.3 gigahertz. The measured peak gain of the horizontal component E phi is on the order of 5 dBi. And again, this is for the isolated element on the ground plane. So the peak occurs in the vicinity of about 50 degrees from broadside with a deep null right at broadside. Here are the measured azimuth gain patterns for the single loop-fed slotted cylinder antenna on the ground plane. And the azimuth pattern is very flat over the band from 1.2 to 1.4 gigahertz. Again, this is the horizontal component E phi, and it's for the isolated element on the ground plane. So over a full 360 degrees, this element exhibits omnidirectional performance. We can also measure the phase of the azimuthal pattern, and we see that the phase is very flat over the full bandwidth. So the pattern is omnidirectional in terms of amplitude, and it has a uniform phase as well. And this is at theta equal 55 degrees. It's the phase of the horizontal component. And again, this is the pattern for the single isolated loop-fed slotted cylinder antenna. Now we show the measured return loss of the center element of the loop-fed slotted cylinder hexagonal antenna array. So we're measuring the return loss of the central element. It's element number 1. The surrounding elements are terminated in 50 ohm loads. It's on the 1.22 meter ground plane. And we see that the return loss is very good. It's well below 10 dB over the 15% bandwidth, from 1.2 to 1.4 gigahertz. So this slide shows the measured mutual coupling from the center element of the loop-fed slotted cylinder hexagonal array. It's a measurement of S12 from element 1 to 2 in the array. And so the measured mutual coupling amplitude is in the range of about minus 12 to minus 14 dB. This slide shows the measured gain patterns for the center element of the loop-fed slotted cylinder hexagonal array. So we're looking at the pattern of the center element with the surrounding neighbors terminated in 50 ohm loads. And the radiation patterns are shown from 1.2 to 1.4 gigahertz. The peak gain is on the order of 5 dBi over the band. It's deep null at broadside at each frequency. And the peak is close to 50 degrees in each case. So with this type of element, we would expect to be able to scan to wide angles. However, we would not be able to steer near broadside. And for cases in which the clutter is strong near broadside, having a null would be advantageous. On the right, we show the measured azimuthal patterns for the horizontal component E phi. We expect to have nearly constant gain, which is shown here, and the cross-polarized component E theta is down by greater than 20 dB over the band. So these omnidirectional patterns were taken at theta equal 55 degrees from broadside. So this type of radiating element exhibits good wide-angle steering capability. On this slide, we vary the number of horizontally polarized loop-fed slotted cylinder antennas that are located in a linear array. We have 1, 3, 5, and 7 elements on the same size 1.22 meter ground plane. And what we want to show is that as we increase the size of the array, that the center element pattern does not change much, which would indicate in a very large array that there would not be any blind spots. So we do see that as the array size grows, that the pattern has stabilized and the peak occurs close to 50 degrees in each case. And so for this case where the spacing is 0.55 lambda, this is at 1.3 gigahertz, we see that this type of an array has good wide angle steering capability. So let's summarize. In this lecture, we have discussed an array of horizontally polarized loop-fed slotted cylinder antennas. We've shown measured array mutual coupling and element gain patterns for hexagonal arrays and linear arrays. And the loop-fed slotted cylinder element demonstrates an element gain pattern with good wide-angle scan coverage. Chapter 13 of the book, Adaptive Antennas and Phased Arrays for Radar and Communications, contains material that can supplement this lecture.